We shall go for one more problem in the lecture, that is problem number 3 and the last one in the lecture, and I have chosen this one because it deals with a practical situation. Many of you who have traveled by ship for the first time have felt unwell, a bit of nausea, vomiting tendencies because of the swinging motion of the ship. So we shall see here exactly why this happens and how we can design a ship to minimize this discomfort of passenger. Problem number 3 here, telling a floating body in stable equilibrium is tilted through a small angle of theta and released. Show that it begins to perform simple harmonic motion. Find expressions for the frequency and time period of the SHM in terms of suitable quantities assumed. Can you relate your answer to the comfort of a journey by ship? So to do the problem, we require some basic introduction into angular simple harmonic motion. I have not taught SHM yet. We shall teach it later when we discuss waves, sound, etc., particularly torsional pendulum, physical pendulum, and so on. For the time being, I shall tell you very briefly when angular simple harmonic motion happens and what is the frequency and the time period of such SHM. Well, if a body performs to and fro oscillation under restoring torque whose magnitude is proportional to the instantaneous angular displacement of the body from equilibrium, then the body is said to be in angular simple harmonic motion. To write it mathematically, suppose for the body in oscillation, the torque acting on it, restoring means directed towards mean position. This torque's magnitude is found to be proportional to, directly proportional to the angular displacement theta of the body from the equilibrium position. That is the criterion for angular SHM. You can write in the next step that the restoring torque tau restoring is equal to a minus sign sitting in the front into a constant proportionality capital C into angular displacement theta from the mean position. In the expression once again, left hand side is the restoring torque acting on this body at an instant at which its angular displacement is theta from equilibrium. C is the constant proportionality and minus sign is sitting because restoring torque acts in the direction of decreasing value of theta. That's why this minus sign. Well, we learned further in rotational mechanics that the torque acting on a body, in this case restoring torque, can be expressed to be the product of moment of inertia of the body about axis of rotation and its angular acceleration alpha. Therefore, I could write angular acceleration alpha, which is second derivative of angular position with respect to time, this equal to the restoring torque, that is tau restoring symbolically, divided by moment of inertia capital I, and putting value from here, this is minus C into theta divided by I. So we are getting here the restoring torque acting on a body in simple harmonic motion can be expressed to be a minus sign sitting in the front, then a constant, that is the ratio of C and moment of inertia. C was the constant in this first equation, multiplied by the instantaneous angular position. It can be shown in detailed calculation that for such SHM, well, let me write it here. This is the criterion for angular simple harmonic motion, and for that SHM, if angular frequency is omega, then can be shown omega square is equal to this ratio capital C by I. Therefore, angular frequency of SHM is coming out to be square root of C upon I. Natural frequency of SHM coming out to be omega upon 2 pi, that is 1 by 2 pi into square root of C by I, and time period capital T is given by 1 upon natural frequency, which is 2 pi into square root of I upon C. So let me highlight once again what we have said. The criterion for angular SHM is restoring torque proportional to angular displacement with a constant proportionality C here. And finally, we have shown the period of such SHM given by 2 pi into square root of I upon C, where I is moment of inertia of the body about axis of rotation and C is the constant appearing in this equation. With this insight into angular SHM, ready for the problem above on a floating body in equilibrium. So I put briefly on the screen our discussion so far and refer to the results of equation number 1 in uppercase Roman numeral because bit of theory for you for quick reference in future discussion. Returning to my question, we shall now show a body in stable equilibrium as it floats in a liquid. I draw the center line, that is the axis of symmetry, on which we take as usual the center of gravity little higher and center of buoyancy little lower position. Center of gravity is G, center of buoyancy is B. Through CG, center of gravity, the force of gravity is acting downwards, and through center of buoyancy, buoyant force is acting upwards. They have the same line of action coinciding with this center line, right? This is FG and this is FB. That was the initial condition of equilibrium, stable equilibrium, and this body is upright. Now suppose, as they have said, the body is disturbed a little by giving it a small angular tilt, maybe in the clockwise sense. So one more figure here by the side, and after the tilt being given, this is the new position of the floating body, and the center line also tilts to the same angle, which is taken to be theta. So let me show it here. I'm once again magnifying this theta. Actual value of theta has to be small if it has to perform simple harmonic motion.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.